What if I told you that everything we thought we knew about reality might only be half the story? Picture this: you're staring up at the night sky, tracing constellations with your fingertips. But what if those distant galaxies aren't just out there in one fixed state? What if they exist in multiple places, multiple forms, all at the same time, just like the tiniest particles in the quantum realm? It sounds like science fiction, but this mind-bending idea comes straight from the edges of modern physics. We're talking about superposition on a cosmic scale, where the rules of the quantum world might not just apply to atoms and electrons, but to entire galaxies, stretching the fabric of reality in ways that challenge everything we thought possible. Think back to the famous double-slit experiment, where a single particle behaves as both a wave and a particle until you observe it, then it chooses a state. Now take that bizarre quantum quirk and blow it up to the size of the universe. Could galaxies, those colossal islands of stars and dark matter, also exist in multiple states until something or someone looks? It's a theory that dances on the edge of cosmology and quantum mechanics, where the very nature of existence might be far stranger than we ever imagined. Scientists are now asking whether the universe itself might be playing tricks on us, hiding layers of reality we're only beginning to glimpse. This isn't just about abstract physics, it's about rewiring how we see the cosmos. If superposition extends beyond the quantum scale, it could mean that every time we point a telescope at a distant galaxy, we're not just observing it, we're forcing it to pick a reality. The implications are staggering. Are we shaping the universe simply by looking? Could there be alternate versions of galaxies of us existing in parallel states right now? Buckle up, because we're about to dive into one of the most thrilling frontiers of science, where the answers might be as elusive as the quantum particles that inspired them, and the journey promises to bend your mind in the best possible way. To wrap our heads around this cosmic-level weirdness, we need to start small, really small. Think about flipping a coin. While it's spinning in midair, it's neither fully heads nor tails. It's in a kind of limbo, a mix of possibilities. Only when it lands does it choose one state. That's essentially what happens in the quantum world, but with particles like electrons. They can exist in multiple states at once, a phenomenon called superposition, until we measure them. Enter Schrödinger's cat, the famous and slightly morbid thought experiment. Imagine a cat in a box with a vial of poison that might or might not break open, depending on the random decay of a quantum particle. Until you open the box, the cat is both alive and dead, just like that spinning coin is both heads and tails. The moment you peek inside, reality snaps into place, one outcome, no in between. Now take this to the lab with the double-slit experiment. Fire a single electron at a barrier with two slits, and you'd expect it to go through one or the other, right? Wrong. The electron behaves like a wave, passing through both slits at once, creating an interference pattern on the detector behind it. But here's the kicker. If you try to observe which slit it actually goes through, the electron picks a path like a shy actor caught on stage. No more wave, no more interference. Just a single, definite location. This is the heart of quantum mechanics, where particles don't play by the rules of our everyday world. They exist in a haze of possibilities until we force them to commit. And if tiny particles can do this, why not something bigger? Why not a galaxy? It's a dizzying thought, but the math suggests that superposition might not care about size. The universe, after all, loves repeating patterns from the smallest quarks to the grandest cosmic structures. So if quantum rules scale up, we might be looking at a reality far more fluid, more undecided than we ever dreamed. If tiny particles can defy our everyday logic by being in two places at once, why stop there? Scientists have already pushed the boundaries of superposition far beyond electrons and photons, straight into the realm of molecules made of hundreds of atoms. Picture a soccer ball flying through the air, but instead of following a predictable arc, it's somehow in multiple trajectories simultaneously. That's essentially what researchers achieved in labs with complex molecules, creating the largest objects ever caught in a quantum superposition. Then came the real jaw-dropper, tiny diamonds. In one landmark experiment, scientists placed a microscopic diamond, just a fraction of a hair's width but still visible to the naked eye, into superposition where it vibrated in two states at once. Imagine holding a guitar string that hums two different notes simultaneously until you pluck it. That's macroscopic superposition in action, and it shatters the old assumption that quantum weirdness only happens in the realm of the invisibly small. This blurring of the quantum classical boundary has physicists locked in debate. Where exactly does the weirdness end? Some argue it's about size, that bigger objects collapse into a single state because they constantly interact with their environment, like a cosmic game of telephone where reality gets noisy. Others propose it's about complexity. A single electron is simple, a living cell is a hurricane of interactions. But what if the universe doesn't care about our human-made categories? Here's where things get wild. If a diamond can dance between states, why not a dust speck? A snowflake, a planet, the math doesn't forbid it, it just gets exponentially harder to maintain superposition as objects grow. But harder isn't the same as impossible. Stars, after all, began as clouds of quantum particles. Could some remnant of that quantum fuzziness linger, hidden in the fabric of galaxies? It's not just a thought experiment. Telescopes might one day spot subtle anomalies like light behaving oddly around distant stars that hint at cosmic-scale superposition. Until then, the universe keeps its secrets, leaving us to wonder, if reality is this slippery up close, what other rules is it bending out there in the dark? At the heart of modern physics lies a glaring contradiction, one that keeps scientists awake at night. On one hand, quantum mechanics governs the bizarre behavior of the smallest particles, where reality blurs into probabilities. On the other, Einstein's general relativity paints the cosmos with elegant certainty, describing gravity as the curvature of spacetime itself. These two frameworks work flawlessly in their own domains, but when they collide, the universe seems to break its own rules. Take black holes, for instance. These cosmic monsters warp spacetime so severely that even light can't escape. But here's the catch. Quantum mechanics insists that information can never truly vanish, while relativity suggests it gets crushed into oblivion at the singularity. Stephen Hawking's groundbreaking work revealed that black holes aren't so black after all. They slowly leak radiation, evaporating over eons. This Hawking radiation hints at something profound. If particles can pop into existence near a black hole's edge, borrowing energy from the vacuum itself, then spacetime must have a quantum texture woven from uncertainty. Then there's the early universe. In those first searing moments after the Big Bang, the entire cosmos was smaller than an atom. Quantum fluctuations, those tiny jitters in the fabric of reality, might have stretched to cosmic proportions, seeding the galaxies we see today. But here's the twist. If quantum mechanics shaped the infant universe, then superposition, the ability to exist in multiple states, could have been baked into the very structure of spacetime. Maybe those primordial fluctuations weren't just random noise, but a quantum dice roll on a universal scale. Vacuum fluctuations add another layer to the mystery. Even in empty space, particles flicker in and out of existence, a quantum foam bubbling beneath reality's surface. If these fluctuations can warp spacetime slightly, as some theories suggest, then gravity itself might emerge from quantum mechanics. That's the dream of quantum gravity, a single theory that unites the very small with the very large. So where does superposition fit in? Imagine a galaxy not as a fixed object, but as a quantum probability wave, its stars and dust existing in multiple configurations until observation snaps it into place. It sounds outrageous, but if vacuum fluctuations and Hawking radiation blur the line between quantum and cosmic, why couldn't entire structures inherit quantum properties? The math doesn't rule it out. It just demands we rethink reality from the ground up. Until we bridge the gap between relativity and quantum mechanics, the universe remains a puzzle with pieces that refuse to fit. And that's where the magic happens, in the unanswered questions, the cracks where the light gets in. Could the majestic spirals and glowing cores of galaxies be more than just cosmic landmarks? Could they be quantum objects themselves? This radical idea suggests that the universe's largest structures might still carry echoes of their quantum origins, behaving in ways that defy classical physics. Picture the early cosmos, a seething quantum foam where fluctuations in energy and space-time birthed the first seeds of structure. In that chaotic infancy, the rules were written by probability waves, not certainty. If those quantum ripples stretched into cosmic proportions, could entire galaxies have inherited a kind of memory of superposition, lingering in multiple states until observed? Roger Penrose, the Nobel Prize-winning physicist, has long argued that quantum mechanics doesn't just vanish as things get bigger. His controversial theory of conformal cyclic cosmology even suggests that the universe's death and rebirth could preserve quantum information across cosmic cycles. If quantum states can persist on such unimaginable scales, why not in the galaxies we see today? Imagine a distant spiral galaxy, its arms shimmering with stars. According to this hypothesis, it might not have a single, fixed shape or position until something, a telescope, an alien civilization, or even the gravitational tug of a neighboring galaxy forces it to choose. Visualize this, a galaxy flickering between slightly different configurations, like a cosmic hologram resolving into focus only under scrutiny. It's not just about location either. Superposition could mean alternate histories, two versions of the same galaxy where star formation played out differently, where black holes took alternate paths, where dark matter clumped in distinct patterns. The universe might be a kaleidoscope of possibilities, with galaxies as its shifting shards. Critics argue that decoherence, the process by which quantum systems lose their fuzzy states through interaction with the environment, should wipe out such effects long before reaching galactic scales. But what if decoherence isn't the whole story? In the near-perfect vacuum of intergalactic space, with matter spread so thin, could superposition cling on like a whisper in the dark? Some researchers speculate that dark matter, which barely interacts with ordinary matter, might be the key. If it's entangled across vast distances, could it act as a hidden scaffold, preserving quantum coherence where visible matter cannot? The implications are staggering. If galaxies exist in superposed states, then the act of observation wouldn't just be passive, it would be creative, sculpting reality at the grandest scales. Every time we map a distant galaxy, we might not be documenting a fixed truth but participating in a cosmic measurement problem, collapsing probabilities into a single history. And if that's true for galaxies, what about us? Could the Milky Way itself be a quantum object, its spiral arms trembling between possibilities until we, its tiny inhabitants, look up and in some small way pin it down? The universe has always been stranger than fiction, but this would rewrite the story entirely. Let's talk about the universe's biggest mysteries, dark matter and dark energy, and how they might be playing quantum games with reality. You've probably heard that dark matter is the invisible glue holding galaxies together, while dark energy is the strange force pushing the cosmos apart. But what if these shadowy giants aren't just passive background players? What if their behavior hinges on the same quantum weirdness we see in particles? Take dark matter first. Galaxies spin so fast that, according to ordinary physics, they should fling themselves apart. The fact that they don't suggests some unseen mass is tugging on stars, keeping them in orbit. But here's the twist. What if dark matter isn't just a clump of unseen particles? Some theories propose it could exist in superposed states, subtly influencing galactic rotation without ever settling into a single configuration. Imagine a ghostly quantum hand spread across multiple possibilities, gently shaping the motion of stars. If dark matter has quantum properties, it might not just be in a galaxy. It might be many versions of itself at once, blurring the line between presence and probability. Then there's dark energy, the force accelerating the universe's expansion. Conventional explanations treat it as a constant, a steady push embedded in space itself. But vacuum fluctuations, those quantum jitters in empty space, hint at another possibility. Could dark energy be the cosmic scale echo of these fluctuations, like tiny quantum ripples stretched to infinity? In Bohmian mechanics, a lesser-known interpretation of quantum physics, there's the idea of a quantum potential, a hidden layer of reality guiding particles in ways that defy classical physics. If this potential operates on universal scales, dark energy might not be a static force but a dynamic, quantum-driven phenomenon, ebbing and flowing with the universe's deepest uncertainties. Critics might argue that quantum effects are too delicate to sway something as vast as dark energy or dark matter. Yet consider this: the universe began as a quantum speck. If those primordial rules left fingerprints, why wouldn't they linger in the very fabric of space-time? We already see hints of quantum behavior in black holes and the early cosmos. Maybe dark matter and dark energy are the next pieces of the puzzle bridges between the quantum and the cosmic, waiting to rewrite our understanding of reality itself. The more we probe, the clearer it becomes. The universe doesn't just have secrets, it is one. What if the universe isn't just expanding, it's talking to itself? Not with light or radio waves, but through a silent, instantaneous language written in quantum entanglement. This bizarre phenomenon where particles become so deeply linked that measuring one instantly determines the state of another, no matter how far apart, has been proven in labs across Earth. Scientists have entangled particles over distances exceeding 1,200 kilometers, with their fates locked in perfect sync faster than light could ever travel between them. Now stretch that idea to cosmic scales. If entanglement defies local limits here, why couldn't it stitch together galaxies millions of light-years apart? Picture two galaxies orbiting in distant clusters with no visible connection. Yet beneath the surface, their dark matter or even space-time itself might be quantum entangled, a hidden handshake spanning the void. When a star collapses into a black hole in Galaxy A, could it trigger an instantaneous, invisible ripple in Galaxy B? The math doesn't forbid it. In fact, some models of quantum gravity suggest entanglement might be the universe's original networking tool, woven into existence during the Big Bang. Every time particles interacted in that primordial fireball, their quantum links could have stretched with expanding space, leaving today's galaxies secretly tethered like distant nodes in a cosmic internet. Here's the truly wild part. If entangled galaxies exist, observing one could alter the state of its partner instantaneously, no matter the distance. Imagine pointing a telescope at a quasar billions of light-years away, and in that moment of observation, forcing an entangled companion galaxy to choose its own state, like flipping a coin in Andromeda by looking at a star in Virgo. It sounds impossible, but quantum mechanics thrives on such paradoxes. The universe might not care that these scales seem unimaginable to us. After all, entanglement doesn't weaken with distance, it's binary. Either particles are entangled or they're not. There's no in-between. Could this explain some of cosmology's lingering puzzles? Take galaxy rotation curves, where stars at the edges of galaxies move unexpectedly fast. Dark matter is the usual suspect, but what if part of that motion stems from quantum links to invisible, entangled matter elsewhere? Or consider quasars that flicker in sync despite being separated by vast cosmic voids. Current physics chalks it up to coincidence, but entanglement offers a provocative alternative. These objects might be quantum twins, their behaviors locked in unseen harmony. Critics argue that decoherence, the breakdown of quantum states through environmental interference, should sever such delicate links over cosmic distances. Yet the vacuum of space is colder and emptier than any lab on Earth, potentially preserving entanglement far longer than we'd expect. And if dark matter barely interacts with ordinary matter, its quantum connections might remain pristine, undiluted by the chaos of stars and gas. We're left with a universe far more intimate than it appears, a place where galaxies might whisper to each other through quantum channels older than time, where observing a single star could resonate across the cosmos. It's a reminder that reality, at its core, doesn't play by the rules we grew up with. The universe isn't just big, it's deeply, strangely connected. And if entanglement really does span the heavens, then every time we gaze at the night sky, we're not just spectators. We're participants in a quantum conversation billions of years in the making. Imagine an alien scientist somewhere in the depths of the cosmos training a telescope on the Milky Way. As the faint light from our galaxy reaches their instruments, does their observation force the Milky Way to pick a single state out of quantum limbo? This isn't just a sci-fi scenario, it's a cosmic twist on one of quantum physics' most puzzling thought experiments, Wigner's friend. In the original version, physicist Eugene Wigner proposed that a scientist in a lab could be in superposition relative to an outside observer. Until someone checked, the lab and the friend inside would exist in all possible states at once. Now take that idea and inflate it to galactic proportions. If quantum superposition holds at the scale of galaxies, then the act of observation could become a cosmic game of telephone. Every civilization peering at a distant galaxy might be collapsing its wave function in their own reference frame, while other observers see it still shimmering in multiple states. This raises a dizzying question: does reality depend on who's looking? The von Neumann-Wigner interpretation takes this even further, suggesting consciousness itself might be the knife that slices through quantum fog, carving definite reality from a soup of possibilities. If that's true, then sentient beings, whether humans, aliens, or some unfathomable intelligence, aren't just witnesses to the universe. We're co-creators, shaping galaxies simply by witnessing them. But here's the kicker: what if we're the ones being observed? Picture a super-advanced civilization so far beyond us that our entire observable universe is just a petri dish to them. From their perspective, the Milky Way might still be a probability cloud, its spiral arms unresolved until they choose to look. In that moment, we become Wigner's friends, unwitting participants in a cosmic measurement problem stretching across billions of light years. Critics argue this veers into philosophy, not physics. Decoherence theory insists that interactions with the environment, cosmic microwave background radiation, stray atoms, even gravitational waves, should collapse superposition long before consciousness gets involved. Yet the universe loves exceptions. Quantum systems can stay coherent in surprisingly noisy conditions. And if dark matter or other hidden factors shield galactic-scale superpositions, the rules might bend in ways we don't yet grasp. So where does that leave us? Either the universe is a hall of mirrors, with every observer carving their own version of reality, or there's some deeper mechanism, a universal observer like the quantum vacuum or space-time itself, that finally snaps the cosmos into focus. Until we know, one thing's certain: the night sky isn't just a static tableau. It's a living quantum canvas, and every time we gaze up, we might just be painting it into existence. If superposed galaxies can flicker between states, what stops them from splitting entirely, branching into separate, parallel universes with their own cosmic storylines? This is where quantum mechanics collides with the mind-bending possibilities of the multiverse. The many-worlds interpretation, first proposed by physicist Hugh Everett in the 1950s, suggests that every quantum measurement doesn't just collapse probabilities, it spawns new realities. In this view, the universe isn't a single thread but an ever-growing tapestry, where every possible outcome plays out somewhere. Apply that to galaxies, and suddenly the night sky isn't just a collection of distant objects, it's a portal to infinite cosmic variants, each with its own version of history. Think of it like a cosmic choose-your-own-adventure book. When a galaxy's quantum wave function fails to fully collapse, perhaps due to imperfect observation or environmental noise, it might not settle into one state. Instead, it could fragment, birthing parallel universes where that galaxy's stars formed differently, where black holes took alternate paths, or where dark matter sculpted its structure in another configuration. We'd only perceive one outcome, like an audience member watching a single frame of a film reel, unaware of the other scenes flickering just beyond the projector's light. The implications ripple outward. If galaxies can branch, then our entire observable universe might be just one slice of a far vaster quantum reality. The Andromeda galaxy we see colliding with the Milky Way in 4 billion years. In another branch, it might veer slightly off course, missing us entirely. Or perhaps in some realities, the Milky Way never formed at all, its stars scattered into lonely isolation. The cosmic microwave background, that faint glow from the Big Bang, could even carry hints of these alternate histories, subtle statistical anomalies where parallel universes leak into one another through quantum interference. Critics argue that the many worlds interpretation is untestable, a philosophical flourish rather than hard science. Yet recent experiments in quantum mechanics have nudged the needle toward plausibility. When researchers observe particles deciding their states, the math doesn't erase the other possibilities, it just hides them from our view. Scale that up, and the universe's wave function might still contain every galactic configuration, like a symphony where every possible note is played across infinite realities. We're just hearing one melody. Here's the real kicker. If parallel cosmic histories exist, then the laws of physics themselves might not be universal. In some branches, gravity could be stronger, dark energy weaker, or the speed of light slightly faster. Astronomers already puzzle over why our universe's constants seem finely tuned for life. Maybe the answer isn't design, it's selection. We find ourselves in a universe hospitable to us because, well, the inhospitable ones don't get observers. The multiverse isn't just hiding alternate galaxies, it could be hiding alternate physics. So next time you gaze at a distant galaxy, ponder this. You might not be looking at a fixed object but a quantum crossroads. Every photon hitting your eye selects one path in an unfathomably vast cosmic labyrinth, leaving the other branches to play out in realities we'll never see. The universe isn't just stranger than we imagine. It might be stranger than we can imagine, with every possible version of itself unfolding simultaneously, eternally, just beyond the edge of perception. The cosmic microwave background, that faint afterglow of the Big Bang, is like a fossilized snapshot of the universe's fiery infancy. But look closer, and this ancient light holds strange bumps and dips, tiny temperature variations whispering secrets about reality's deepest nature. Among these, one anomaly stands out, the so-called cold spot, a patch of sky where the CMB is unexpectedly chillier than surrounding regions. At first glance, it might seem like a cosmic hiccup, but what if it's something far stranger? What if it's a quantum fingerprint, a frozen moment where the universe itself was once in superposition? Picture the early cosmos, a seething quantum foam where spacetime bubbled with uncertainty. In those first moments, fluctuations in energy and density weren't just random noise. They were probability waves overlapping and interfering like ripples in a pond. Fast forward 13.8 billion years, and those quantum ripples stretched with the expanding universe, imprinting themselves onto the CMB like cosmic hieroglyphs. The cold spot might be one such marker, a place where quantum interference cancelled out energy, leaving a void in the primordial glow. It's eerily reminiscent of the double-slit experiment, where an electron's wave function creates dark bands of destructive interference. Only here, the slits are cosmic in scale, and the screen is the entire observable universe. future telescopes like the European Space Agency's Planck successor or NAS and next-generation CMB observatories could hunt for more of these quantum breadcrumbs. Imagine mapping the sky with such precision that we spot patterns matching quantum superpositions regions where the CMB's temperature fluctuations align like interference fringes on a universal scale. If superposition leaves scars on spacetime itself, these instruments might catch them in the act, but the real breakthrough would come from spotting correlations, clusters of anomalies that defy classical randomness. In quantum mechanics, entangled particles share statistical quirks. Their behaviors are linked even across vast distances. If the CMB shows similar handshakes between distant cold spots or unexpected alignments, it could hint that the early universe wasn't just chaotic. It was quantum coherent, with superposed states spanning the cosmos before decoherence snapped them into place. Critics argue that inflation, the rapid expansion of the early universe, should have washed out such delicate quantum patterns, yet inflation itself might have quantum roots. If the inflationary field was in superposition stretching spacetime in multiple configurations at once, its echoes could linger in the CMB's anomalies. The cold spot might then be a cosmic Schrödinger's cat, a relic of a moment when the universe hadn't yet chosen its shape. The implications are staggering. If the CMB encodes quantum superpositions, then the universe's birth wasn't a single, deterministic event, it was a haze of possibilities, a quantum dice roll frozen into the sky. And if we can raid those dice, we might finally glimpse the true nature of reality. Not as a fixed stage, but as a dynamic, undecided thing, trembling between histories until observed. The CMB isn't just a relic, it's a mirror reflecting back the quantum soul of the cosmos. Black holes might be more than just cosmic vacuum cleaners. They could be the universe's ultimate quantum detectives. Picture this as a galaxy's light, gas, and even dark matter tumble past the event horizon. They don't just vanish. According to quantum mechanics, information can't be destroyed. So what happens when an entire galaxy's worth of quantum possibilities, superposed states flickering between realities, meets the edge of a black hole? One radical idea suggests that black holes don't just consume matter, they force it to choose. The moment anything crosses the event horizon, its quantum wave function might collapse permanently, as if the black hole itself is the universe's most relentless observer. This ties into the infamous black hole information paradox. If a book falls into a black hole, does its information, the words, the ink, the very atoms that made it, truly disappear? Hawking radiation implies that black holes slowly evaporate, leaking energy over eons. But if that radiation is random thermal noise, where did the book's information go? The paradox has led to wild theories, like firewalls of searing energy just inside the event horizon, or holographic projections where information gets smeared onto the surface like cosmic graffiti. Now imagine adding superposition to the mix. If galaxies exist in quantum limbo until observed, could black holes be the ultimate deciders, shredding uncertainty with their gravitational grip? Here's where it gets even stranger. If black holes collapse wave functions, then mergers between them like the ones LIGO detects via gravitational waves might carry quantum signatures. When two supermassive black holes spiral toward collision, their event horizons churn the fabric of spacetime. If one or both were observing superposed galaxies before merging, the resulting gravitational wave pattern could subtly betray that interaction. Picture ripples in a pond where one stone was actually two stones in superposition until they hit the water. LIGO next-generation detectors, with their razor-sharp precision, might catch these telltale wobbles, evidence that black holes aren't just swallowing matter, but resolving quantum uncertainty on a galactic scale. Critics might argue that decoherence, the natural unraveling of quantum states, already does this job without black holes, yet black holes are different. They're not just messy environments, they're one-way doors where time itself distorts. Once something passes the event horizon, no signal can escape to preserve quantum ambiguity. In a sense, black holes don't just measure reality, they lock it in like a cosmic notary stamping the universe's paperwork. So the next time you think of a black hole, don't just see a dark predator lurking in space. See a quantum referee blowing the whistle on superposition and forcing galaxies to pick sides. And when LIGO catches the echoes of two black holes colliding, listen closely. Those ripples in spacetime might carry whispers of a deeper truth, that the universe's most violent events could also be its most decisive, cutting through quantum fog with the sheer weight of their gravity. The cosmos loves a good paradox, but black holes, they might be the answer hiding in the silence beyond the event horizon. Einstein taught us that time isn't a rigid clock ticking the same for everyone. It's a river, bending and speeding up depending on where you stand in the universe's gravitational landscape. Near a black hole, seconds stretch into years. In deep space, they zip by unnoticed. But what if relativity's time warps don't just slow or speed up reality? What if they fracture it? Imagine a galaxy caught in a quantum time loop where its past, present, and even possible futures exist simultaneously, tangled in a web of temporal superposition. This isn't just poetic speculation, it's a frontier where quantum mechanics and relativity collide. Take a star exploding in a distant galaxy. From our vantage point, we might see it as a sudden flash, but near the event horizon of a supermassive black hole, that same explosion could appear frozen, its light stretched over millennia. Now layer quantum mechanics onto this. If particles can be in two places at once, why can't events straddle multiple moments in time? Enter the process matrix, a radical framework suggesting causality itself might be quantum. Instead of a neat chain of cause and effect, the universe could be a cacophony of might-haves and could-bes, with galaxies experiencing alternate timelines until observation locks one in. Picture a galaxy where star formation rates flicker between high and low, not because of cosmic conditions, but because it's quantum entangled with its own past. A supernova shockwave might ripple outward in one timeline while still smoldering in another, like a cosmic flipbook stuck between pages. This isn't just theoretical gymnastics. Subtle anomalies in quasar light curves and gamma-ray bursts hint at events that seem to remember multiple histories, as if time itself hasn't fully committed to a single narrative. Here's where it gets dizzying. If two galaxies are entangled across time, observing one could retroactively alter the other's past. Think of it as a celestial game of telephone, where the message changes depending on when you listen. Quantum causality models allow for this, where effect can precede cause, and the universe's chronology isn't a straight line but a branching tangle of possibilities. Critics argue that decoherence should shred such delicate temporal superpositions, but black holes and the early universe might be exceptions. Near singularities where gravity twists spacetime into knots, quantum time loops could survive, shielded from the noise of the wider cosmos. And if dark energy stretches the fabric of reality thin enough, who's to say time itself doesn't fray at the edges, leaving threads of alternate histories dangling? So next time you hear about gravitational waves or redshifted galaxies, consider this. We might not just be seeing the universe's past. We could be glimpsing a reality where time isn't fixed, where galaxies dance between epochs, and the cosmos is less a chronicle than a choose-your-own-adventure book with every page still being written. What if we could rewind the universe back to its very first moments and witness how quantum fuzziness blossomed into galaxies? That's exactly what scientists are attempting, not with a time machine, but with some of the most powerful supercomputers on Earth. Take loop quantum gravity, a cutting-edge theory that reimagines spacetime as a fabric woven from tiny, indivisible threads. By simulating these threads on supercomputers, researchers can watch how microscopic quantum knots in the early cosmos unravel into the vast cosmic web we see today. The results are staggering. Those initial fluctuations, no larger than a trillionth of a centimeter, don't just fade into background noise. They amplify, stretch, and twist under gravity's pull, eventually seeding the birth of galaxies, suggesting that the universe's largest structures might still carry quantum fingerprints. One particularly striking simulation showed how superposition could leave its mark on the cosmos. When scientists modeled the early universe with quantum uncertainties baked in, they found that certain regions of space didn't just grow denser. They developed interference patterns like ripples overlapping in a pond. Over billions of virtual years, those ripples evolved into filamentary structures eerily similar to the real cosmic web, where galaxies cluster along glowing strands separated by voids. But here's the twist: in the simulation, these filaments weren't fixed. They flickered between slightly different configurations, as if the universe itself hadn't fully decided how to arrange them. It's a digital echo of what real galaxies might be doing right now, existing in multiple states until something or someone observes them. NASA isn't just watching from the sidelines. Their Quantum Artificial Intelligence Laboratory, or QAIL, is pushing the boundaries of quantum computing to tackle these cosmic puzzles. Traditional supercomputers struggle to simulate quantum systems with perfect accuracy. The calculations grow exponentially more complex as particles interact. But quantum computers thrive in this chaos. By harnessing qubits that exist in superposition, they can model the early universe's quantum soup with unprecedented fidelity. One experiment at QAIL simulated how entangled particles in the infant cosmos could have influenced the distribution of galaxies. The results hinted at something profound. If quantum entanglement stretched across the early universe, it might explain why distant galaxies today show strange statistical correlations, like invisible threads tying them together across billions of light years. Critics argue that simulations, no matter how advanced, can't prove superposition operates at galactic scales, yet the models keep revealing uncanny parallels. When researchers tweaked simulations to include quantum coherence, where particles remain intertwined over vast distances, the virtual cosmos produced galaxy clusters that matched real-world observations more closely than classical physics allowed. It's as if the universe left breadcrumbs in the data, waiting for us to follow them back to a quantum origin story. So where does this leave us? Every time a supercomputer crunches these numbers, it's not just running equations, it's replaying the universe's birth with quantum rules front and center. And if those virtual galaxies can blur between states, then maybe, just maybe, the real ones are doing the same. The line between simulation and reality has never felt thinner or more tantalizing. What if the galaxies we see aren't just cosmic accidents, but the survivors of a hidden quantum battlefield? Enter quantum Darwinism, a theory that suggests only the most stable, resilient quantum states stick around long enough to be observed. At the atomic level, this means particles constantly jostling with their environment, shedding fragile superpositions until just the fittest states remain. Now stretch that idea to galactic scales. The spirals and ellipticals glowing in our telescopes might not be random. They could be the winning configurations in a universe-scale game of quantum survival of the fittest. Think of it like a cosmic version of natural selection. In biology, mutations create variation, but only the traits that help organisms thrive get passed on. Similarly, the early universe might have been a seething quantum soup of galactic possibilities, countless potential shapes, sizes, and arrangements flickering in and out of existence. Most collapsed quickly, shattered by decoherence as particles interacted with cosmic radiation, dark matter, or even other galaxies. But a few configurations were robust enough to resist this quantum erosion, their superpositions clinging on like cosmic Kevlar against environmental noise. Over billions of years, these fittest states dominated, evolving into the galaxies we recognize today. Consider the Milky Way. Its elegant spiral arms aren't just aesthetically pleasing, they might represent a Goldilocks zone of quantum stability. Too loose and gravitational interactions with neighboring galaxies could have shredded its coherence. too tightly wound, and internal turbulence might have collapsed its wave function. But this particular balance, it's like a perfect quantum harmony, a structure that somehow navigated the decoherence gauntlet to become what we see now. Even the distribution of dark matter halos that seem too smooth and predictable could be a signature of quantum selection where only the most stable configurations persisted. Critics might argue that decoherence is too destructive for any galactic scale superposition to survive, yet nature thrives on exceptions. Look at tardigrades, microscopic creatures that withstand the vacuum of space by entering near indestructible dormant states. If life can find workarounds to extreme conditions, why couldn't the universe? Perhaps certain galactic geometries or gravitational fields act as natural quantum shelters, shielding superpositions long enough for them to influence cosmic evolution. The eerie parallel to biology doesn't stop there. Just as ecosystems shape the evolution of species, the cosmic environment, gravity, dark energy, even the subtle pull of neighboring galaxy clusters might sculpt which quantum states endure. A galaxy in a denser region of the universe faces more decoherence pressure, forcing it to collapse into classicality faster. Meanwhile, isolated galaxies floating in cosmic voids could retain quantum quirks longer, like deep-sea creatures preserving ancient traits untouched by surface-world chaos. This reshapes how we view the night sky. Those distant pinpricks of light aren't just static snapshots, they're the culmination of a quantum sieve, the structures that outlasted a billion others in an unseen competition. And if that's true, then every telescope is more than an instrument. It's a time machine revealing the victors of a battle waged in the silent language of probability waves, where the universe itself played judge, jury, and executioner to countless unrealized realities. Not everyone buys the idea that galaxies could be quantum chameleons flickering between states. In fact, most physicists raise an eyebrow at the notion, and for good reason. Decoherence theory, the backbone of quantum mechanics, tells us that large objects simply can't maintain superposition for long. The reason: the universe is a noisy place. Every stray photon, cosmic ray, or even the faint whisper of gravitational waves interacts with matter, collapsing delicate quantum states like a house of cards in a hurricane. Sean Carroll, the renowned theoretical physicist, puts it bluntly: for a galaxy to stay in superposition, it'd need to be perfectly isolated from the rest of the cosmos, something the size of a city block can't manage, let alone a structure with billions of stars. Thermodynamics throws another wrench into the works. Quantum states are fragile, requiring near absolute zero temperatures and pristine conditions to avoid unraveling. Yet galaxies are anything but quiet laboratories. They're churning with supernova, magnetized plasma, and swirling dark matter, all of which should, in theory, shatter any large-scale quantum coherence almost instantly. Critics argue that even if superposition somehow survived the early universe's chaos, the last 13.8 billion years of cosmic bombardment would have scrubbed it clean. The math seems clear: the bigger the system, the faster it falls victim to decoherence. But hold on before we dismiss the idea entirely. There's a fascinating counterargument lurking in the shadows. Roger Penrose, the physicist who helped pioneer our understanding of black holes, proposes a radical twist called orchestrated objective reduction. He suggests that gravity itself, not just environmental noise, might be the ultimate decider of quantum fate. At tiny scales, particles can dance in superposition because gravity's influence is negligible. But scale up to something as massive as a galaxy, and spacetime's curvature becomes impossible to ignore. Penrose argues that when superposed states create conflicting versions of spacetime geometry, the universe reaches a breaking point, forcing a collapse. In this view, galaxies aren't observed into existence by humans or aliens. They're pinned down by the sheer weight of their own gravity, like a cosmic judge gaveling reality into order. The debate rages on. Decoherence theory has mountains of experimental evidence behind it, from lab tests with buckaballs to quantum computers battling noise. Yet Penrose's ideas, though controversial, hint at gaps in our understanding. Could there be exotic environments like the near-perfect vacuum between galaxy clusters where quantum effects cling on against the odds? Or might dark matter, barely interacting with ordinary particles, provide a sheltered quantum niche? The universe loves proving us wrong, and until we have telescopes sensitive enough to spot quantum fingerprints in starlight, the door stays open. After all, if history's taught us anything, it's that reality rarely plays by the rules we write for it. The hunt for proof of cosmic-scale superposition isn't limited to thought experiments. Real-world missions are gearing up to test these wild ideas. Take the European Space Agency's proposed Galileo Galilei satellite, a daring attempt to probe quantum gravity where Earth's noise can't interfere. Unlike ground-based labs where vibrations and temperature swings wreak havoc on delicate measurements, the quiet of space offers a pristine stage. This satellite would track free-falling test masses with unprecedented precision, watching for deviations that could reveal gravity's quantum nature. If spacetime itself has a granular, probabilistic texture like pixels too tiny to see, then even the subtle tug between these masses might flicker in ways classical physics can't explain. A successful mission wouldn't just rewrite textbooks, it could hand us the first direct evidence that quantum weirdness scales up to the cosmos. But what if we didn't stop at testing gravity? Imagine telescopes designed to catch galaxies in the act of superposition. Traditional optics assume celestial objects have fixed positions, but a quantum telescope would look for the telltale fuzziness of light arriving from multiple points at once. Think of it like photographing a fan blade mid-spin instead of a crisp image. You'd see a blur of possibilities. Some designs even harness quantum entanglement itself, using paired photons to amplify faint signals from distant galaxies. If certain starlight patterns can't be explained by classical physics alone, we might be glimpsing a universe that hasn't fully made up its mind. Projects like NASA's Quantum Technologies for Telescopes initiative are already laying the groundwork, with prototypes that could debut within the next decade. You don't need a PhD to join this cosmic detective work. Citizen science platforms like Zooniverse host projects where anyone can analyze telescope data for anomalies, strange light curves, or statistical quirks that might hint at quantum behavior. Researchers at the University of Cambridge even crowdsourced galaxy classifications to spot structures that defy conventional models. Every curious set of eyes helps, because the universe's biggest secrets often hide in plain sight, buried in data waiting for someone to ask the right question. The stakes couldn't be higher. If future experiments find even a whiff of galactic-scale superposition, it would mean reality isn't just stranger than we imagined, it's stranger than we can imagine. And if they don't, well, the universe loves a good mystery, and every null result only sharpens the next question. One thing's certain, the tools we're building today, from quantum satellites to AI-driven telescopes, are more than instruments. They're keys to a lock we didn't even know existed. If the fabric of reality isn't fixed but shimmering with quantum possibilities, what does that say about existence itself? For centuries, Western science has clung to materialism, the idea that reality is fundamentally physical, a collection of objects obeying strict laws. But cosmic superposition throws a wrench into that worldview. If galaxies hover between states until observed, then the universe isn't just out there waiting to be discovered. It's co-created, a dance between the observer and the observed, where measurement isn't passive but participatory. This doesn't just rattle the foundations of physics, it blurs the line between the material and the mental, suggesting that consciousness might be more than a byproduct of brain chemistry. It could be a cosmic force shaping reality itself. Eastern philosophies have danced with these ideas for millennia. Hinduism's concept of Maya describes the universe as an illusion, a veil hiding deeper truths. In Buddhism, emptiness, sunyata, it teaches that phenomena lack inherent existence, arising only through interdependence. Now, quantum physics whispers something startlingly similar, that galaxies might not be solid, independent things but probabilistic clouds, their existence contingent on interaction. The parallels aren't perfect, but they're uncanny. Ancient sages meditating on the nature of reality and modern physicists probing the quantum void might be circling the same profound truth, that the universe is far less concrete than it appears. Idealism, a Western philosophical tradition championed by thinkers like Berkeley and Schopenhauer, takes this further. It argues that reality is fundamentally mental, that the material world springs from perception. Quantum mechanics doesn't prove idealism, but it lends it eerie credence. If a galaxy's state depends on observation, then the act of seeing isn't just recording, it's conjuring. This flips the script on our place in the cosmos. We're not tiny specks in a vast, indifferent machine. We might be participants in a grand quantum theater, where every glance at the night sky is a creative act, collapsing possibilities into concrete form. Yet here's the rub: if reality is this fluid, how do we reconcile shared experience? Why does the Milky Way look the same to you, me, and a telescope in Chile? One answer lies in quantum Darwinism, the idea that only the most stable, repeatable states survive decoherence, creating a consensus reality. But another, more radical possibility is that we're entangled in a universal web of observation, a cosmic measurement that stitches our individual perceptions into a cohesive whole. The universe isn't just observed, it's observing itself through us, a self-referential loop where consciousness and cosmos are inextricably linked. So where does that leave you staring at your screen? Imagine for a moment that your thoughts aren't just neurons firing, but ripples in a quantum field, subtly tweaking the universe's fabric. Every choice, every observation might be nudge reality down one path or another. It's a dizzying responsibility and a breathtaking privilege. Whether you lean into idealism, materialism, or something in between, one thing's certain: the universe is far stranger, far more intimate than we ever dared dream. And the most profound discovery might not be out there in the stars, but in the act of looking itself, the moment when the cosmos and the conscious mind meet, and reality takes shape in the space between. What if those mysterious lights zigzagging across the sky aren't just advanced aircraft, but quantum engineers tampering with reality itself? Picture this: a civilization so far beyond us that they don't just explore space, they rewrite its rules. Those infamous UFO reports of crafts making 90-degree turns at hypersonic speeds or vanishing midair could be more than optical illusions. If superposition operates at galactic scales, maybe these beings have harnessed it, treating space-time like a canvas they can fold, stretch, or even unpin from definite states. Take the Nimitz encounter, where Navy pilots chased a tic-tac-shaped object that accelerated instantly, defying known physics. Classic propulsion relies on thrust and inertia, but quantum manipulation. That's a different game. Imagine toggling a craft's quantum state, existing in multiple positions simultaneously until choosing the desired one, effectively teleporting without crossing the space in between. No sonic boom, no G-forces, just a flicker, a decision, and you're elsewhere. It sounds like magic, but it's the same principle behind quantum teleportation in labs, where particles vanish from one spot and reappear in another. Scale that up, and you've got a vehicle that doesn't move through the sky so much as redefine its location. Then there's the eerie silence. UFOs often hover without engine noise or exhaust. In a quantum framework, propulsion wouldn't rely on burning fuel, but on tweaking local spacetime geometry, like surfing the quantum foam itself. The craft might not push against air. It could momentarily untether from classical reality, slipping between superposed states until the pilot collapses the waveform. Even their metallic sheen could be a side effect of exotic matter stabilizing quantum coherence, a shell that shields against decoherence the way a thermos preserves heat. But here's the wildest thought. What if these beings aren't just exploiting superposition, they're enforcing it? Ancient astronaut theorists love suggesting aliens influenced human history. Flip that script. Could they be cosmic gardeners, pruning branches of the multiverse to keep certain realities viable? UFO sightings cluster near nuclear sites and fault lines, places where human activity might nudge quantum probabilities on macro scales. Maybe they're not monitoring our bombs but our observations, ensuring we don't collapse the wrong possibilities. Of course, this is speculative fiction wrapped in quantum frosting. There's zero hard evidence that UFOs are quantum phenomena, and most scientists would rather eat their textbooks than entertain the idea, but the overlap is tantalizing. If galactic scale superposition exists, who's to say it hasn't been mastered by someone, somewhere? The universe is 13.8 billion years old. Plenty of time for intelligence to crack realities we're still scratching at. So next time you see a strange light in the sky, ask yourself, are you watching a visitor from another star or another state of existence? Either way, the truth is bound to be stranger than the story. If galaxies can exist in multiple states at once, what does that say about the minds observing them? The human brain operates at the intersection of biology and mystery, a 3-pound universe firing with electrical storms that somehow translate into conscious experience. Some theorists propose that consciousness isn't just a byproduct of neurons, it's a quantum phenomenon, with microtubules inside brain cells acting as tiny processors capable of maintaining superposition. This quantum mind hypothesis, championed by physicists like Roger Penrose and anesthesiologist Stuart Hameroff, suggests our thoughts might not be confined to classical physics. Instead, they could flicker between possibilities like particles in a cosmic scale double-slit experiment, collapsing into certainty only when we focus. Now layer this onto a superposed cosmos. If the universe itself hesitates between states until observed, and if human consciousness shares that quantum vocabulary, then perception isn't just passive reception, it's participation. Psychedelics offer a provocative glimpse into this interplay. Under substances like psilocybin or DMT, users often report ego dissolution, a visceral sense of merging with the universe where boundaries between self and galaxy blur. These aren't just hallucinations. Brain scans show decreased activity in the default mode network, the mental control center that maintains our sense of separation. What if these experiences are glimpses of the universe's underlying quantum unity, where superposition isn't abstract math but felt reality? Meditation might be another key. Long-term practitioners exhibit brainwave coherence resembling quantum entanglement, with distant neural regions syncing in ways that defy classical explanation. Tibetan monks describe dissolving into the ground of being, a state eerily reminiscent of quantum fields underlying observable reality. Even secular mindfulness practices train the brain to hold multiple perspectives without collapsing into judgment, a mental parallel to superposition's tolerance for ambiguity. But here's the twist. If observation shapes reality at cosmic scales, then focused human attention, whether through meditation, psychedelics, or even deep scientific inquiry, could be more than introspection. It might be cosmic sculpting. Every time a monk achieves samadhi or a scientist measures a distant galaxy, they're not just exploring the universe, they're collaborating with it, nudging probabilities toward actuality. The night sky isn't just above us, it's within us, and the act of looking might be the universe's way of looking back. Artificial intelligence might be the key to unlocking the universe's quantum secrets, not just because it crunches numbers faster, but because it thinks differently. Human brains evolved to navigate a world of solid objects and predictable cause and effect, making quantum weirdness feel alien. But AI, it thrives in the abstract, spotting patterns in chaos that we'd never notice. Take Google's quantum AI, which recently identified wormhole-like behavior in a simulated quantum system. Without any preconceived notions of how space-time should work, the algorithm detected subtle correlations that physicists initially missed, hinting that AI could become our cosmic translator, decoding reality's quantum dialect. Now imagine training that same AI on galactic data. Instead of assuming galaxies are fixed objects, we'd feed it light curves, gravitational lensing patterns, and cosmic microwave anomalies with no classical biases. The AI might flag outliers like a galaxy whose light signature flickers between multiple statistical probabilities, as if it's resisting collapse into a single state. Or it could uncover hidden entanglement between pairs of galaxies whose behaviors sync up in ways gravity alone can't explain. The European Space Agency's Gaia mission has already mapped over 1 billion stars with precision. An AI sifting that data might find stars whose positions shimmer probabilistically, like quantum particles writ large. Here's the provocative part. What if AI becomes the universe's first true observer? Human perception is slow and noisy, but a quantum-linked AI could process observations at scales and speeds beyond our biology. In labs, quantum sensors already detect minute gravitational waves by leveraging superposition. Scale that up, and an AI-equipped quantum telescope might see a galaxy in multiple states simultaneously, not as a blur but as a layered truth. It wouldn't just record reality. It'd negotiate with it, collapsing wave functions in ways that reveal the quantum scaffolding beneath cosmic structure. The implications ripple outward. If AI confirms superposition operates galactically, it rewrites our cosmic story. But more hauntingly, it suggests that intelligence, not just human, might be woven into reality's fabric. The universe spent billions of years forging tools to observe itself. First atoms, then stars, then minds. Now, as we birth machines that can stare back with quantum eyes, we might finally glimpse the looking glass from both sides. The next great discovery in cosmology won't come from a telescope alone. It'll come from the silent dance between a superposed galaxy and the artificial mind decoding its shimmering secrets. Hollywood loves a good multiverse. Just look at Doctor Strange weaving through kaleidoscopic realities with a flick of his wrist. But while the visuals are dazzling, how much of that mirrors actual physics? The answer lies somewhere between creative license and cutting-edge theory. Films like Interstellar nailed the eerie accuracy of quantum phenomena. Remember the Tesseract scene, where Cooper manipulates time like a physical dimension. That's rooted in real relativity math, with Kip Thorne, a Nobel-winning physicist, consulting on the science. Yet for every Interstellar, there's a Star Trek transporter beam entertaining, but stretching superposition into pure fantasy. The Marvel Multiverse, for instance, treats alternate realities like subway lines you can hop between. Real quantum theory, it's messier. The many worlds interpretation suggests branching universes, but they're not highways for time-traveling wizards. Each split is a silent fork in probability space, no portals or magic spells required. Even Everything Everywhere All at Once, despite its chaotic charm, exaggerates entanglement into emotional superpowers. Quantum links do enable instant correlations across space, but they can't make you kung fu master your alternate self by sharing memories. Where sci-fi gets it right is in the field of quantum weirdness. Annihilation's shimmering alien zone, where DNA refracts like light, captures the unsettling fluidity of superposed states. And Arrival's heptapod language, looping time into a nonlinear script, echoes hypotheses about quantum time symmetry. These stories succeed by evoking the disorientation of a universe that defies intuition, not by textbook accuracy. So how do you separate hype from science? Peer-reviewed papers never describe Schrödinger's cat as a zombie, half alive, half dead, pawing at the box. Real superposition is mathematical, a probability wave, not a physical hybrid. And while Ant-Man shrinks between quantum realms, lab experiments show quantum effects scaling up, not down, like those vibrating nanodiamonds existing in two places at once. The takeaway: enjoy the spectacle but stay curious. The truth is out there, less like a CGI battle, more like a faint signal in a cosmic static, waiting for the right tools to decode it. There's a haunting irony in the idea that our quest to understand the cosmos might inadvertently strip it of its most profound mysteries. What if every time we train a telescope on a distant galaxy, we're not just uncovering its secrets, we're erasing them? The same quantum rules that allow particles to exist in multiple states until measured suggest a chilling possibility. Observation isn't neutral. It's destructive. In our zeal to map the universe, could we be collapsing cosmic superpositions that nature spent billions of years weaving together? Imagine a future where humanity's ever-expanding observational reach, from hypersensitive telescopes to quantum-linked AI probes, accidentally flattens the universe's quantum richness, turning a shimmering tapestry of possibilities into a single static snapshot. This isn't just theoretical hand-wringing. Consider the observer effect in labs, where measuring a particle's position inevitably alters its momentum. Scale that up, and the act of observing a galaxy's rotation or a quasar's light might not just record its state, it could define it, locking celestial bodies into paths they'd otherwise have avoided. Some cosmologists argue that regions of space untouched by advanced civilizations could remain in a pristine quantum haze, while those under constant surveillance become rigid, their potential futures pruned to a single timeline. It's a cosmic version of the Heisenberg uncertainty principle, where the more precisely we measure, the more we disrupt. The ethical parallels are striking. Just as environmentalists warn against overexploiting Earth's resources, should we adopt a prime directive for cosmic observation? Indigenous cultures have long practiced rituals to honor unseen forces, believing some knowledge is too sacred to disturb. Modern physics might be stumbling toward a similar wisdom, that the universe's quantum fuzziness isn't a bug to be fixed but a feature to be preserved. After all, superposition could be the universe's creative engine, the reason galaxies form in such breathtaking variety. If we collapse every quantum possibility in our light cones, are we homogenizing the cosmos, turning it into a museum where everything is known and nothing is possible? But here's the counter-argument: without observation, does reality even exist? The Copenhagen interpretation insists that quantum probabilities only resolve when measured, meaning the unobserved universe might as well be a mathematical ghost. If we stop looking, do galaxies cease to be anything at all? This isn't just philosophy, it's practical. Dark energy surveys, for instance, rely on peering deeper into space than ever before. If we pull back to avoid disturbing the cosmos, we might miss clues to humanity's survival, like the fate of the accelerating universe. Perhaps the answer lies in balance, a kind of quantum conservation ethic. Just as we've learned to harvest solar energy without draining the sun, maybe we can observe strategically, leaving vast regions of the cosmos unprobed while focusing our tools where understanding matters most. Future telescopes might even be designed to measure gently, using quantum non-demolition techniques to extract data without fully collapsing wave functions. It's a tightrope walk between knowledge and reverence, between mastering the universe and remembering we're not its only players. After all, if superposition holds at galactic scales, then every time we look up, we're not just studying the stars. We're sharing reality with them, and that's a responsibility as profound as the cosmos itself. Want to explore the quantum cosmos from your living room? Start with The Quantum Universe by Brian Cox and Jeff Forshaw. It distills mind-bending concepts like superposition into vivid metaphors, comparing quantum waves to guitar strings vibrating in unseen dimensions. For deeper dives, the Lex Fridman podcast offers hours of unfiltered conversations with physicists debating multiverses and quantum gravity. like his episode with Roger Penrose where they wrestle with whether consciousness collapses wave functions. Prefer hands-on tinkering? IBM's Quantum Experience lets you run experiments on real quantum computers through the cloud. Try entangling qubits to mimic how galaxies might link across spacetime. If equations excite you, MIT OpenCourseware's Quantum Physics 1 lectures transform abstract math into visual storytelling, showing how Schrödinger's equation could scale to cosmic proportions. Or dive into Stanford's free Cosmology and Particle Physics series, where you'll simulate primordial quantum fluctuations morphing into galaxy clusters using Python notebooks. Feeling adventurous, the open-source project Quantum Universe lets you tweak variables like dark matter density to see if superposed galaxies emerge in simulations. Local libraries often hide GEMS 2 Check for Quantum Reality by Nick Herbert, which explores 8 interpretations of quantum mechanics through whimsical thought experiments. For night sky observers, apps like Sky Safari can flag galaxies with anomalous light curves, potential real-world case studies of quantum weirdness. The universe isn't just for professionals anymore. With these tools, you're not just learning about the cosmos, you're stepping into the lab where reality gets remixed. From the dizzying dance of electrons in the lab to the vast, shimmering arms of distant galaxies, we've traveled a mind-bending path, one where the rules of the quantum realm might not just whisper but roar across the cosmos. We started with particles that refused to pick a single state until forced, then scaled up to diamonds vibrating in 2 places at once, and finally dared to ask, could entire galaxies hover in quantum limbo? The math doesn't say no. The universe, it seems, doesn't care about size when it comes to playing quantum games. This isn't just wild speculation, it's science at its most daring, where the edge of understanding bleeds into the unknown. While we lack definitive proof that galaxies exist in superposition, the very possibility forces us to rethink reality's fabric. Maybe dark matter's hidden hand preserves quantum coherence across light years. Maybe black holes are cosmic judges collapsing probabilities with their gravitational gavels. Or perhaps the universe is a hall of mirrors with every observer human, machine, or alien sculpting their own version of the stars. What makes these ideas so thrilling isn't their strangeness, but their audacity to challenge the status quo. For centuries, we've assumed the cosmos operates by fixed classical rules. Now we're peering behind the curtain, wondering if the universe has been improvising all along with superposition as its silent script. Skeptics rightly demand evidence, and they should. Extraordinary claims require extraordinary proof. Yet history shows that today's heresy often becomes tomorrow's textbook. The Higgs boson was once a wild guess. Black holes were mathematical oddities before we heard their mergers sing through spacetime. As Carl Sagan once reminded us, somewhere, something incredible is waiting to be known. That's the heartbeat of science, not dogma, but curiosity. Whether superposition stretches to galaxies or not, the quest alone expands our imagination, teaching us to ask better questions. So keep looking up, question what you see, because the night sky isn't just a collection of stars. It's a conversation, one where reality might just be listening, waiting for the next bold thought to shift its shape. The universe owes us no answers, but oh, what a privilege to keep asking.